String theory was once considered the leading candidate for a theory of everything, promising to unite quantum mechanics and general relativity. But over time, it has faced intense scrutiny. Today we'll explore the specific reasons why string theory is considered by many experts to be impractical and largely debunked. String theory proposes that instead of particles, the fundamental constituents of the universe are tiny, one-dimensional strings that vibrate at different frequencies. These strings are said to exist in up to 11 dimensions beyond our ability to observe. The theory suggests that these vibrating strings create the different particles we observe. In essence, everything in the universe, matter, forces, even space and time, is made of these vibrating strings. It sounds groundbreaking, but the theory quickly runs into problems. First, despite its mathematical beauty, string theory has yet to provide any experimental predictions that can be tested. For example, particle accelerators like the Large Hadron Collider have been unable to detect any signs of extra dimensions or string-like particles after years of experimentation. Physicists have long searched for tangible evidence that could support string theory, but without any direct observations or experimental data, string theory remains purely theoretical and speculative, making it difficult to test its validity. Another key issue with string theory lies in its complexity. The theory's equations are so complex that they require an intricate mathematical framework, which is extremely difficult to connect with physical reality. The theory introduces up to 11 dimensions, most of which are completely unobservable with current technology. One of the biggest criticisms of string theory is the landscape problem. The theory predicts a vast array of possible solutions, over 10 to the power of 500 different vacuum states or configurations of the universe. This makes string theory incredibly flexible but also highly problematic. It can be made to explain anything, rendering it useless for making specific testable predictions. The theory's ability to explain everything essentially means it explains nothing. Scientists argue that a valid theory should be able to make clear, specific predictions that can be confirmed or refuted through experiment, something string theory has been unable to achieve. String theory's lack of falsifiability, the inability to test or disprove it, has caused many in the physics community to turn away from it. This makes string theory more of a mathematical abstraction than a practical scientific theory. In contrast, simpler theories like loop quantum gravity have emerged as strong contenders. Unlike string theory's complex and abstract framework, loop quantum gravity is focused on the quantization of space-time, providing a more grounded and experimentally testable approach. Loop quantum gravity offers a much simpler way of combining general relativity and quantum mechanics, and importantly, it is designed to be testable, with clear predictions that can be verified through experiments, unlike string theory's reliance on unobservable extra dimensions. One of the fundamental issues with string theory is that its extra dimensions are hypothesized to be so small, on the order of the Planck length, that they are far beyond the reach of any technology we currently have. Without the ability to observe these dimensions, string theory remains a concept that can't be directly tested. Even with advanced instruments, like the Large Hadron Collider, no evidence has emerged to support the existence of extra dimensions or string-like particles. This lack of tangible evidence has made it increasingly clear that string theory may be a dead end in the quest for understanding the universe. As we move forward, physicists are focusing on theories that can make predictions we can test, theories grounded in observable phenomena. Unlike string theory, these theories aim to explain the universe in ways that connect to real-world data, paving the way for future breakthroughs. More recently, the investigation of six-dimensional space-time offers a more tangible possibility of providing physics with the elusive unified field theory everyone is seeking. String theory, despite its intriguing possibilities, has failed to deliver on its promise. Its complexity, lack of experimental support, and inability to make testable predictions have led many physicists to abandon it in favor of simpler, more grounded approaches. The search for a unified theory of the universe continues, but for now, string theory has been left behind in favor of theories that can bring us closer to answering some of the most fundamental questions about the cosmos.